So thank you very much for having me. I know it's very late and you're probably very hungry. So I'm really sorry that this has to be at this time. But well, let's see how it goes. I know. So we'll see where we get in an hour. I mean, I have tried to like reduce this presentation. I made a new one for an hour, but I'm not quite sure it's for an hour. But we'll see. So inference. So how many of you are familiar with this idea of inference or using inference from data? A few, okay. A few are not. I mean, I will try not to be very hardcore, like mathematical, in the sense of being very technical about what I want to do. And if anybody wants to know more about the details, you can ask me, of course, but in an hour, I don't have time to give you like a full course on this, but hopefully you learn something new. So let's see, I selected, I'm going to talk like, just because this is sort of like a lecture seminar, I'm not sure what this is, but let's say it's like a lecture for the school. So I'm going to give you like an outline. So I'm going to present you with two problems, okay? Two problems that are related to complex systems science. One is related to more like complex networks. The other is more like related to obtaining networks and models from data. But before going to the problems, I will give you I will brief you on what I mean by using inference to approach these two problems. So let's go to the problems. And first, let me show you this. So what you see here are a female and a male of this Drosophila melanogaster. And this male is courting the female, right? And it's chasing the female, and it's just like playing like a song, just like by vibrating one of the wings, right? And then in this other one, I have a cousin of Drosophila, and he's doing exactly the same thing. He wants to court the female, but instead of, I can replay the movie. Instead of like chasing the female, what this other fly is doing is, is standing in front of the female, right? And not, I don't know if you can appreciate it, but it's not flipping its wings. It's just like silently, like just displaying the wings, which are apparently very nice. I don't know. Okay. So the thing is that the purpose is the same. They want to find a mate, okay? But they are doing very different things, right? They are behaving very differently. And I have a friend who has the suspicion that some of these differences can be explained because of differences in the way the neurons are connected inside the brain of these two very, very similar friends. They are very, very close cousins. So, okay, so he has given me, he says, I'm not on, it's not only that I have this hypothesis, but I think I can show that this is true. Because I have a way of empirically getting the map of connections between the physical map of connections between the neurons in the brain of a fly, right? This is data that was published this year. I mean, it became available more than a year ago, but I mean, I think it was published this year. They published like many papers on this connectome. And this is the connectome of an adult fly, right? Of an adult female fly. And very soon they will release the male one. And he's just like, oh, well, I can produce these objects that are large, that are 130,000 neurons with millions of synaptic connections between them, but I can get it, right? It's a lot of work, but I can get it for the two cousins. And from there, I want to find the answer. So now we have a problem, right? We have these two connectomes, right? And we want to know what's different between the two, right? Well, first of all, what I have is that these neurons here are not labeled. I don't know which one is which in the two connectomes, right? And this means that I have to solve, no, this is not, okay. I think I have to put it here. Okay, that I have to solve a problem that is known as the problem of network alignment. So I give you these two networks, right? The blue one and the red one. And I ask you, can you tell me which node in the blue one corresponds to which node in the red one, right? Your answer, if this is not working, is probably going to be something like, okay, I can tell you, definitely I can tell that C is 2, for sure. It only has one connection. I can tell that A is 1. B and D, I mean, I cannot tell. with this information, I cannot tell you. I would need more information, or I would need maybe directionality in the connections. But you understand what the problem is and what I want to find. Well, it turns out that this is a very, very old problem, right? People started, like chemists were very interested in knowing whether two molecules were isomorphic, right? The two molecular structures. And so they thought like, oh, they have the same graph, the same molecular graph, and I want to find whether they have the same molecular graph. And they, they invented some algorithms. This is a very hard problem, a very hard problem. But you can think that, well, there were ways to at least find approximate solutions to this. Actually, it's a very important problem in many areas of science. For instance, it's important for computer vision, in which you want to track images and you want to track points. And you want to know in this image, the point moved to this other pixel in here. And according to the vicinity, I can represent this as a graph and then make the matching. So this is something for which there are algorithms to solve this problem. There are better and worse algorithms, but at least there are approaches to do this. It's important for people who want to understand whether like data de-anonymization techniques work. Like for instance, when they give you a data set about like users using like a social network, right? And they give you users using another social network, right? They worry about whether you can tell which one is which across the two social platforms. Because sometimes even if they release the data in principle, de-anonymizing the users, sometimes the topology is so correlated that you can actually tell who is who. So they have to invent other ways to give you the data so that you cannot tell who is who. So there's another application. I'm not interested in those ones, but just for you to get an idea. So my problem is if I have two or more, in reality, I will want to have more. The more I have, the better. And labeled graphs, can I find the mappings between the nodes that are the different networks that I have? And there, as I said, the problem is all, right? So I want to go from this, my observation, to this other picture here in which I know who is who. And these are just like, again, these are simple networks. I'm just like giving you the purple one as a guideline. So for you to see, like, this is when I don't know how they are labeled. This is when I can map them correctly. Okay. Everybody understands the problem. So as I said, it's very old. If somebody wants to know more, there are several reviews. I think what's funny about this area is that only people typically look at only one part of the literature. So this is a very good review for, like, I guess, methods developed for maybe computer vision and other things. And there are the reviews that are good for methods used for like biological networks. But for some reason, they don't overlap very much. Well, I know it's crazy how many things there are. But I'm going to give you like just two options of what's out there. So one thing is that what I want to map the nodes across my networks, right? My suspicion is these two networks are topologically correlated, meaning that they share the connections, because otherwise I cannot define my problem very well, right? I'm going to try to align them based on topology alone. And the thing is, well, I can construct maybe some vector that characterizes my nodes, right? And if it's unique based on the topological properties of the graph, then maybe just comparing these two vectors, then I can align them, right? So one possibility is to look is to build these vectors for each node, taking into account in the way they participate in different motifs in the network. So this is what is called graphlets. I mean, so they're just motifs, right? So my node is involved in this motif and it's not involved in this other motif, and like blah, blah, blah. And I can build a vector like this and then compare using some sort of metric for comparison. Okay. Another option, right? This is a very well-known one, is what it's called the quadratic assignment problem. So essentially, I have two matrices, right? And if I suspect that I can map one adjacency matrix into the other, I can do that by having a permutation of the rows and the columns. I mean, it depends on whether it's symmetric or, I mean, it's a directed graph or not, but you can understand it. Just will have like a permutation that will map me this one into this one if they are identical, or if there are some differences between the two, I can still make a mapping because there is a correlation, a topological correlation. Then I would want, what I will want to know that this is a good mapping of this onto this, is to minimize the error between the two matrices or to maximize this. It's the same, okay? It's the same as minimizing the error because the squares are constants, and then I just have the negative term between the two, and it's the cross product, right, between the two. So I can also do this. This is nice. There are fast ways to do this. Now, what are the problems with these approaches, right? I'm trying to use this and it doesn't work. I mean, I'm not sure this is the thing. Maybe it's this one. Okay, my apologies. It's just I want to. No, it's not gonna. No, not gonna work. No. Okay. Well, so what are the problems? Okay, several. And one that I think is very important. So I only presented you with two methodologies, right? But the two of them are not using the same metric to assess whether my mapping is good or not. This you could say, well, it doesn't matter. Well, I mean, I don't know. They use different metrics. Then the other one, which is interesting to me, is that they are only defined for pairs of networks. Like I can very well define this problem of like just having a permutation of an adjacency matrix and compare it with the other. But if I have more, with which one do I have to compare? I don't know. The first one, the second one, the third one. If I have 10, I mean, that's not very well defined. Now, also like there's the problem, like if there's more than one alignment and they are like similarly good according to your metric, I mean, why should you get one instead of the other? If there is noise between the two networks, I mean, well, also, how can you, and also in the end, right? Remember my problem, the problem of my friend is like, I want to align these connectors and then they wish to tell what's different between the two. So the thing is like, these methods don't have any like statistical generative process behind them. So how can I make statistics on what's different and what's not? I don't think you can, but I mean, somebody has tried. But certainly very good results, I can tell. Okay, this was problem number one. Now, problem number two, I have another friend who's very interested in learning about whether it's possible to construct a model, right? That will tell me what's the number of people that will go from one place to another. So from my origin, usually the data that I have is maybe the population, which is like the mass, if you want, and some other information, right, that I can get from, say, like maps or other indicators about the importance of this place, yeah, the distance between the 2 points, and then the population at the destination and some other information about the destination, whether it has schools, whether it has hospitals, I don't know, things like that, right? And so what's out there, right? This certainly it's not a problem that my friend has come up with. Like people have been interested on these things for a while. So we have, oh, this is not very good. Let me move this. Is there a chance that I can, how do I do this? I want to, I cannot, no, és que no veig el ratolí. No el veig, I per què s'està? Sí. Sí que es pot, però no sé com. No veig el ratolí. Aquí. Aquí. Bueno, no sé, ho mourem per aquí.
O dona-li a la pestanyeta aquesta d'aquí, la primera.
Aquí?
Sí.
A veure. Ja lo baixo aquí? Sí. Molt bé. Vale, pues no. Sorry. Okay. So what's out there? No, this is not working. So there's the full spectrum. The first models to be proposed today are the so-called like gravity models, in which like, well, I assume that say like the flow is going to be proportional to the importance originally, to the importance of the point of the destination, right? And maybe to the number of people that are in the origin, right? So it's going to be proportional to something that is the product of those things. It turns out that the population of a place is already a good indicator of how many hospitals or cinemas or movies that are going, or shops that are going to be there. So you can just use the population divided by some power of the distance between the two, right? So that if they are very far apart, it's very unlikely that you're going to go, right? I mean, it's very close, it's more likely, yes? And, or variations of this, like exponentials of this, well, a certain family of things that are called gravity models. And in the other side of the spectrum, there's this like deep gravity models. And this is a recent paper, oh, no, for some reason it doesn't show, by Simini and other people. I think it's 2024 or 2023 in Nature Communications. Well, so the thing is that they use this deep gravity model. So they use deep learning. They use like a ton of features. Look, that is using very few features, just like populations and distances. And here they're using like, I don't know, 40 or something like this, right? They do lots of stuff and then they make predictions on it. Okay. And then it's more like, well, I mean, yeah, all this like deep learning stuff works apparently better, but I mean, at the first model, I like it because it's simple. And I mean, is there a way in which I can tell one model is better than the other? And one of the things that happens here, like in the problem before, is that many studies, they look at different metrics to assess how good the model is, right? It's awful because I mean, really? Like, so one paper shows one, another paper shows another one. I mean, whatever is more convenient to you. They use something called like CPC, like common part of commuters, which is like a disaster because it just focuses on like large flows. So as long as you predict the large flows fine, and you do all the others absolutely wrong, then you're good. I mean, well, that doesn't make any sense to me, but I mean, these things happen. So they use different metrics. The other is, well, like the problem is like, well, my simple models are easy to interpret but are not very accurate. The very complex ones that I cannot interpret seem to be way more accurate. Seem to be. We'll see later about what this means. And also, again, like if I have different models that are like that explain my data similarly good, I mean, what should I do? Well, so okay, so I have a similar question. So what we need, what I would want, right, is a way to assess, okay, the best mapping between the nodes, right, in the best problem, or the best model for flows. And I want this, a way to assess it that does not depend on some heuristic that I came up with. Like, oh, I'll do it like this because I think this is, no, I don't know. It's not that I don't want to think, but I want to think of a general framework that will do this, not for me to like decide, no, this is the way I should do. Later on, probably this will be clear what I mean by this. Then also, I want a way to compare them, right? A way to compare models like alignments or models for flows, doesn't matter, that it's robust and it does not depend on the context. It can, I want to use a formalism, right, in general, that is not any different in conceptual terms for the alignment or for the flows. I want to use the same framework. I have to be able to define it in general terms, right? And I don't want these models, I mean, to have to evaluate these models based on some external whatever. Okay. Piece of data, metadata for networks or other things. No, I want the same framework to already give me the metric of how good this is. Okay, good. And last, and it's a consequence of this, right? I also want the model to tell me when I'm finding a model that makes sense and when I'm finding a mapping that makes sense, right? So if there is a lot of noise, it's obvious to all of us that it doesn't make any sense to try to find a model because I shouldn't be able to find none. But many methods out there to find models will still give you one. The question is like, of course, I mean, this doesn't make any sense. It's the answer that the method should give you is like, okay, no, there is too much noise here. There is no way you can find a model that is meaningful, at least using an automated task, unless you know a priori what the model should be. And if you know that, then you don't have to use any of it. But if you don't, I mean, at least you want something that satisfies at least this basic thing, right? That is when there is too much noise, I don't want a model, or when the networks are too different, I don't want a mapping, right? Okay. So what I think is that using this inferential approach, you can find an answer to all these challenges, to all of this. Well, I mean, some people will argue with me, but at least you can find a much better answer than you had before. For me, it's a very good answer. Okay, and what do I mean by inference? I showed pictures sometimes. So, like when we do inference, right? Now, just to be clear, it's not like everything is parameter free and it comes out of like nowhere. No, I'm making some assumptions about like my reality or how data or some model that makes sense for my data, right? In the case of the policeman and this, like I'm telling you, his his model of reality is, oh, you know, when it's at night and I find a person wearing a blindfold with like a bag and like the glass is broken, probably he's trying to break in or he already broke in, right? This is his model of reality. His model of reality is like, oh no, when this thing happens, right? Like usually people go out at night because they have to go to a masquerade, but they forgot something in their shops and they break in because they want to buy something. I mean, this is not their model of reality. And the reason why that's not their model of reality, because experience probably tells him that that's not their model of reality. But still, the thing is that probably he will try to like bring him to like into custody or something like this. And it's because the decision that he's making, it's because of the model of reality that he has. So we have a, and these will be our assumptions. And any decision that we make later on will be because of the assumptions we made. Now, if the assumptions that we make are not good for the data we have, then it doesn't matter that I use an inferential framework, that probably my answer is going to be very bad. Right? But I mean, I just want to say that it's not only using inference, but also knowing about the hypothesis that you are making to do that. Okay. So like general things, and I don't know, I should know what time it is. It's already 26 minutes.
Yeah.
Oh, wow. I started late or I'm just going very slow? Well, I'm going very slow. So I will just go very quick. So now, that's just very basic. So we have some data, okay? And we want to say something about a model, right? Yeah. So in Bayesian inference, what I want to compute is something that is called the posterior. So it's the plausibility of my model given my data. Okay, this is what I want to compute. This is what my main object, right? So in problem one, right, my data are going to be the adjacency matrices. Maybe I have some other information about node labels that is going to make my task easy. Not identities, but labels, general labels like groups or things like this. And then my model are going to be the node mappings, right? Something like this. So in the second one, so my data are the observed flows, right? And my model are going to be the dependency between the variables, right? How the flows depend, the number of people going from one place to another is going to depend on the population, the distance, and other variables that I could have. Okay, awesome. So in this formalism, right? The most plausible model, right? It's the best model that I can find. It's the model that maximizes this posterior. Okay, then we will talk about how I compute this, but just for you to know the rules that I'm going to use. So the best alignment is the one that maximizes the posterior of my alignment given my adjacency matrices, and the best mathematical model is the one that maximizes the posterior of the model given the data points. Okay, perfect. Now, nice thing, and I'm telling you for those who have a background in physics, the nice thing about this is that there is a direct correspondence between the canonical ensemble in statistical physics and conditional probabilities, right? So I can express the posterior in terms of an energy function and then use all the algorithms that I know are useful to sample a space of a system with a specific Hamiltonian can be used to sample over the space of parameters of my model, okay? And I sample from the posterior, and this allows me to find the minimum energy, but also very nicely, I could compute, say, like the partition function, right? Just by sampling over the space, meaning I can compute integrals over this. And this is very nice because I can run statistics over my models, not only have to get the best model, but if I have several that are competing, then I can use them all, yeah? Which is very nice. So I don't have to compromise if I don't need to, unless I want to give a very final answer. Okay, so now that we know like the basics, like I will want to compute this posterior. To be able to do that, what I need is what's called a generative model. Okay, what's a generative model? Okay, that's a lot of text, I know, but it's just if anybody wants to read. So a generative model is a model that assigns probabilities to my observations. Okay, that's what's a generative model. From that, I can build my probabilities, right? If I typically, all my models will assume that my observations are independent. So I have like a product of probabilities. And from there, I can construct the objects that then I might have to integrate over some parameters or whatever I have to do and find my energy, right? But my starting point necessarily is a model that will assign probabilities to my observations. And the assumptions of this model, right? In all the assumptions that I'm making, it's what I'm going to put in the model. And everything else is free, okay? So typically, the more you know about your system, the more specified your model is, right? And the less you know, the less specified. Okay? Okay, but that's nice. In here, there is all my input about my assumption, and it's very clear, right? Well, if you know what you're doing, it should be clear. Okay, perfect. So, how do you operate in practical terms? So first you use Bayes theorem in the sense that I want to compute this object here, that's my posterior, but I use Bayes theorem and I can put it in terms of the likelihood, the probability of my data given my model. I'm telling you my model is a generative model and it gives probabilities to each one of the data, right? So I have a product of like for data point 1, this is the probability according to the model, data point 2, probability, data point 3, so on and so forth. Then in the prior, I put all my a priori expectation about like my model or my model parameters, right? If I kind of like, I have a group model and I know that there are 4, maybe I just want to look at models that have 4 groups, right? Things like this. And this is the evidence that for the purposes here, it's just a normalization constant, okay? Then, an important thing about this. So if I take the log of the posterior, so I've told you, in a model in which all events are independent, all observations are independent, if I take the logarithm, this will scale with the number of points, right? Because I will have a sum of logarithms of probabilities, yes? So this is something that scales with the number of points, like is an extensive part with the number of points, and this one is not. So essentially, if you have a large number of points, the prior probably washes away, yes? Because this is the main contribution. If you have a lower number of points, then this usually plays a role, yes? Okay, good. As I said, I'm not sure I will be able to explain everything, okay? But I mean, I will explain this. So once I've done, so I use Bayes theorem, then I use my generative model, right? The specifics to compute my likelihood here, and I select the prior, okay? Third, now, this is maybe a little technical for people who have never learned about this, but typically my model can have many parameters, but in the end, I'm just interested in one of those things. So for instance, a typical example is a community detection in networks. I don't know if you're familiar with this problem, but I have a network and I want to find the best division of nodes into groups that best explain my network, right? The only thing I care about is the division into groups, and any other parameter in my model needs to be integrated out because I'm not interested in it. So to find my answer, I will need to integrate with respect to other. We will see what this means a little bit for our case here. And the fourth part is once you have this, then you use it and see how well you're able to do it. Well, you define your algorithm, blah, blah, and you use it. Okay, perfect. Okay. So you remember my 2 examples? First one, network alignment. Okay, so let's go to network alignment. And that was now I have time to go more slowly. Okay, so as I said, we already know about the problem, right? This is our problem. We want to go from here, my observations, to this other position in which I know who is who in each one of the networks that I see. Yes? And my motivation originally was like, I'm going to have objects like this, like they are brains, right? They are connectomes. And I have all the synapses between my neurons. And so I have something like this in this cartoon. Like in general, what I will do, like this is the typical thing, is that I represent each one of these neurons that are very spindly, some of them, as a dot, as a node. And the synapses, right, will give me the connections. This will be a directed graph. Actually, it's like a multi-graph, a multi-directed graph, because I have many parallel edges, right? As many as synapses between pairs of neurons. But for simplicity, for today, it will be like 1 to 0. There is at least one synapse or there are 0, okay? But we have another working with like, multiple connections, but I mean, I don't have time to really go into the details. Okay, so what's my generative model? Okay, so now a very simple model. So we will assume that there is so my connectons, right, of the fly or of any other thing, I will assume that they are actually copies of some blueprint of our connectome, okay? So essentially, they are doing all these flies, right? They are doing the same thing, right? They are flying, they want to court a female if they are a male, or a female they want to be courted, probably or not, I don't know. But I mean, they want to feed, they hear things, right? They see things. I mean, they all work the same, and because of historical reasons and lots of knowledge that there is in the field, these brains are connected in a very similar way, okay? So it is not so crazy to think that there is some blueprint, right? Some master blueprint of the brain of a fly, right? Or of any other animal. And each individual will have a brain that looks like that one, more or less, right? So this more or less for us is like, okay, it's a copy with some errors, okay? So I have that all my brains are copies of the blueprint. And then once I have this, right, instead of mapping this network to this network to this network, I map them to the blueprint, right? This is very nice because if I can do this, then I can do it for 2, for 3, for 5, for 1 million if I want, right? Because I'm mapping not against one another, but against the blueprint, right? Now, the price that you pay is that now my model has two things, right? One is like say, if you want permutations, imagine that I label them from 1 to I don't know how many there are in here, to 9, right? All of them. And I just have to find permutations of these labels, right? Between them. But in addition to that, right, of what are the mappings of the nodes, then I have to also learn the blueprint, right? But what I gain is not only the recurrent inferior blueprint, which is actually, it happens to be of interest for neuroscientists, but also that I can do it with many networks. And actually, the larger the number of networks that I have, the larger the number of observations, the better my blueprint inference is going to be because I have more information. Okay. So perfect. Let's do this, right? So my model actually now it's like this. So I have my blueprint, right? And then I can make two types of errors, right? One, when there was no connection, I put 1, or when there was one connection, I just don't copy it, okay? This is just super simple model, right? You have a probability for each edge in the blueprint, you copy it with probability P and Q, sorry, no, 1 minus Q, and for each non-edge, I put a 1 with probability P. Okay, so it's kind of simple, right? Given the blueprint, I know very well how can I give probabilities to any network that I see. Okay, so my model parameters are, just to go back to it, the matching of the nodes with the latest, the blueprint, and then these other two. What I'm interested in as a solution are only these two. These two are just, parameters that I need in my model, but that I will have to integrate out because they are not part of my solution of what I want to find out. Okay, perfect. So now this is terrible, but I mean, so the thing is, this is my posterior, right? This is my model, the blueprint and the permutation set. These are my observations. And these things here, right, are the integrations over the parameters I'm not interested in. So I can, fortunately for me, this one is an easy integral, so I can do it. And I end up with lots of text. The important thing is here that I will be able to put this in this shape, and that this energy function depends on this O thing, this O011 or 10. These elements here are just, if I stack the networks, right, I can then see how many connections overlap, right? How many ones are ones all the time, how many zeros are zeros all the time, right? And then I compare them with the blueprint, right? If I have a 1 in my blueprint, do I also find a 1? So this thing here is like the number of ones in the blueprint that are also 1 in the network, right? So it's like how many edges are stacked with the blueprint. These one are the zeros in the two of them. These are the largest numbers. The others, the cross ones, You want to minimize those, right? You want to maximize it and minimize it, right? In a good mapping, right? You want the blueprint to be as similar to your networks in a way, right? And then, because in this way, you will have that the networks are as similar as each other as possible. So, okay, with this formalism, right? I have my inference, I have my energy, I can sample over alignments, I can get the best energy if I want, the minimum one, or I can look at many alignments that are out there, many possible permutations and blueprints, and see what are the statistics of that. Yes? Okay. So, okay, I'm checking the time. So I'm not doing this for the fly, because for the fly we have like the one, and very soon we will have another one. So clearly we are not there yet. We got lots of money to do it, so it will be done, but I mean, not yet. So what we did first was we will look at this connectome of C. elegans. Do you know what C. elegans? Does it ring a bell to anyone? It's a model organism. It's a little nematode, like a worm, and it's transparent, and it has been studied like it was the first connectome ever like obtained, the first full connectome back in the 80s. And it's a very good model organism for aging, for response to heat shock, right? When you hit an organism too much. So it's nice because we know a lot of things. And there was this paper, like about 4 years ago, in which they got the physical connectome between the neurons at different stages of development. Okay, starting like first it's a larva, and then it's an adult. And this is a very nice data set. This is a small connectome of about, the full nervous system has about 300 neurons, but the brain has like 220, something like this. So we decided, okay, let's look at this and see if we get at least the densest networks, right? Can we align them or not, right? This is a very hard problem because as the brain develops, the number of synapses increases, right? So it means that here at these stages, still there are some connections that have not appeared yet and that are here. So this makes it hard for us because it's not in our generative model. Our generative model, it's more like we have adults and we generate many copies. But let's see how we do. Okay, let's see how we do even. Okay, so what am I showing you here? Okay, so each one of these rows, it's a connector, okay? And each one of these, I'm not sure if you can see the detail, but in the x-axis there are neurons. And these are different types of neurons, like motor neurons, muscle neurons, sensory neurons, different types of neurons that you can define in terms of what they receive inputs, they are connected to muscle. Okay, so if it's blue, okay, it means that it's correctly mapped. And I know it because I have the ground truth in this case, right? It's correctly mapped. If it's orange, it's not, okay? So this is the best, if I look in terms of energy, this is the minimum energy that we could find. Well, it's not bad, it's 64% accurate, it's not that bad. But clearly, there is one that is very wrong. Do you know? And you would say, like, well, I mean, how can it be? I mean, for sure you can find something that's better than this, right? It can be, but it's no, it's actually, this is the minimum energy we could find. Can you think of any reason why this could happen? What was going on here? I know this is a very hard question. We have a brain, we have one of the three connectomes that is completely wrong, and yet it gives me a very good energy. So even if it's the alignment is wrong, the overlaps between the connections are very high. Can you think when this could happen?
What are the differences?
At 13 states. Yeah. It could be related. It's a physiological thing. No? No one? There's a disease? No, they were healthy. You're thinking, like, why is she asking me this? No, I mean, it took us a while to understand why this was happening. Okay. So what we found, and I'm giving you a hint, is that in here, like if I look, like we will start to like, what's going on? So if I look at this neuron and I see which one it's paired with and it's wrong, I see that it's pair, so the errors go by pairs. So this one should be mapped to this one, and it's mapped to this one, and this one, it's mapped to this one. So the errors go by pairs. So I make, it should be like this, and I cross them. Can you think of a situation in which this happens a lot of times? Exactly. It's left-right symmetry. So this brain has left-right symmetry with small differences. But for in other instances, when we run the algorithm, maybe we find another one is flipped, right? So this symmetry is so good, right, that even the small errors sometimes make it that left is more similar to right in one of the instances, right? In one of them. Now, what happens if this is for the best one, right? The best one. But what happens if I sample over alignments? Instead of considering just the best one, then maybe the second best one is already very good, right? Let's see what happens. And here. Oh, if I consider just sampling over alignments, right, instead of considering just the one, then, wow, suddenly it doesn't much better. Because it turns out that by chance, this has a very low energy, but all the other ones that have also very good energies actually have much better alignments. They are more similar to like my reality, and they know what's left and they know what's right. Okay, so this is very nice. And nice because see, if I had not used inference, I wouldn't be able to find this. This is what I would find. And we used other methods, and they get confused all the time, right? It's not so bad if you say like in biology, it's not so bad. Well, I'm making the mistake with left and right. I mean, it's not like it's the end of the world. I mean, it's still like working very decently, but it doesn't. I mean, in other situations in which you don't know the solution, it's like you probably would be very confused. Well, so that's what we managed to do. I mean, we have many other examples that we've done. Now, the nice thing about this type of approach is that it does not only work for connectomes. We've done it for social networks and for other things using exactly the same generative model, and even and that, well, that tells you that maybe this idea of footprint is not so crazy after all, even for other types of networks. Okay, and for the networks for which it doesn't work, which I've also checked, are the ones for which we know that this idea of copying from a blueprint is not a good one. It's not a good one. Okay, cool. So I think I already said this. And botany, okay, there's a misspelling here. So for the last one, and I have like 12 minutes, but I will try to make it less so that you have time to ask questions. So I promise you, it's the last thing that I'm going to talk about. A generative model for symbolic regression, and I use example, which are my flows. Okay, so where were we here? We had our flows, and my friend is very interested in obtaining a model, right, for flows. For flows, mobility flows between two places, and given some information on the distance between the two places. And well, we have the simple models and we have the very complicated models, and we are like, okay, the simple models, I love them because they are easy to look at, but they are not very accurate. But the other ones are way too complicated. I mean, and the thing is like, how can I compare these two actually? I mean, I'm very confused about the metrics that I'm using. My friend has a lot of questions. Okay. So the thing is, the question first is, I told you, this is about Bayesian inference. So can I develop like a Bayesian framework to obtain models from data, right? In the previous problem was like, can I use like Bayesian inference to find good alignments? The answer is yes, you can, with a very simple generative model, right? And so you can. Now, can I do it for this problem as well? Using same framework, but now, of course, this is a completely different data. So I have to think about something else. So the thing is you can, and you can build what we call a machine scientist, right? A machine that will get data, will do something, and will give you like models, right? So we are not the first ones to do this. I mean, there's a lot of history about this, and I forgot to put here, I thought there was here. There is some paper in Quanta magazine about 2-3 years ago. It's very nice because there has been lots of work on this, but people only tend to read, what happened yesterday or the day before yesterday. But people have been working on this since the 80s. And there are lots of things that have been done in this area, and I think it's very interesting to see like how people like even like develop the notion of, can I develop like a robot scientist, like a machine scientist that is going to get data and give me models for the data, right? And that can help scientists find, especially now that when we have lots of data and we don't even know where to start. Okay, good. So now this is, yeah, I'm sorry, I'm not even going to try, but I mean, there is something here. So what's the formalization, right? So to infer like models from my data, right? And my models are going to be F, right? Some analytical model like an exponential, a quadratic function, the sine of whatever, a logarithm, right? Any closed form mathematical form. And I have my observation, right? It's going to be my dependent variable and my independent ones, my function. I will assume that my observation is the function times some error. And here comes my generative. My generative model is one such that it's the noise that I apply to each point is independent. So I have independent observations and it's Gaussian distribute. Okay. So that the probability of each one of my observations given my model is going to be something like this. Yes. And then my likelihood is just the product of these probabilities. Yeah. Okay. So then my posterior of my model is going to be my likelihood, which I can construct with this, my prior, I'll talk about it a little bit more, and my normalization constant. Yes? So it's a very simple, it's just like a regression, yeah, like in a regression problem, right? In which you use, when you solve like the estimation of coefficients in a linear regression, you are assuming that your errors are Gaussian, right? So in here, it's the same, but instead of having a linear function, you have any function that you want to have, right? It's a generalized regression, if you want, or symbolic regression. And in other fields, they call it equation discovery or systems discovery, but well, anyway. Okay, so now, after some work, it turns out that my posterior here I can express in terms of this, okay? The first part is something that is called the Bayesian information criterion that you can compute from the data. For now, don't worry too much about this. This comes from the integration over parameters of my function. You have this term. And then you have the log of this prior. Okay, now in this prior, now in here you have an opportunity, right? To make your automated this equation discovery machine to behave as scientist-like as possible, right? Because as scientists, we have this, or we don't have it, but we learn it. We learn it when we are like students and grad students. We learn that if I can use a simple model to explain my data, I will prefer that one over a more complex one. Yes, even if its explanation not as good, right? I would prefer a line to explain 20 points than a polynomial with 20 coefficients, right? I mean, clearly, I would prefer the line. Now, this idea of parsimony of my model. I mean, I cannot just go to the machine and say, okay, look at each one of the models and say, this is more parsimonious than this one. It's not going to work. So I have to tell my machine, and I tell my machine my a priori expectations on the complexity of my model via my prior. And this prior, right, it's going to be very high for simple models and very low for very complex ones. And what we did actually is we obtained it from Wikipedia. But it's not that we just use the expressions from Wikipedia, it's that we collect statistics from Wikipedia and we want our prior to reproduce these statistics, right? Not the functions themselves, but the number of products, number of exponentials, number of logarithms, things like this. Okay, perfect. And then, so I have my energy function, then I have to sample over my space of models, and to do that I represent my functions as trees, which is a very nice thing, because then once I have trees, then I can propose changes of trees and sample over the space of possibilities. Perfect. So my robot, right? My machine scientist is going to be able to assign plausibility to models, right? This is very important because then I can compare models, right? Yeah, the one with the largest posterior is my best model, but I can still sample over the posterior as before. How? using some sort of metropolis algorithm to do that. Okay, perfect. So I'm not going to show you how well the model works. I'm going to go directly to the mobility flow. So I input this data to my machine scientist, and I see what I get. And this is the kind of models that I get. So this is the logarithm of the flows, and you see these two models look very different, but there is one thing in common. What do you see in common? In common, they have products of masses, right? There is something that above the fraction, it's like a product of masses or mass plus a constant, right? And below there is a function of distance. And this is very similar to gravity models, right? The only thing is that it's a little bit different in the sense that it has some constants and some exponents that we show that are around between 1 and 2, right? They are not very different. And this is for different places, different mobility flows across different states in the US. So you got a very consistent prediction for all of them, right? So this is very nice, right? The thing that the machine scientist is telling me is that this gravity idea is a very good one, okay? It makes a lot of sense, but it needs a little bit of readjusting, okay? The reason why it was fitting so poorly is because you were forcing it, you were constraining it too much. If you let it flow, then, you could find these other models that are more predictive. But I cannot really, I would not be able to tell you right now that this one is absolutely better than the other one, right? Because they give me similar predictions based on their parameters, but they have many commonalities, right? This gravity idea is a very good one. Actually, and this is the last thing I'm showing you, if I compare them, so these are, I was saying, different metrics, right? This is relative to the gravity model. Whatever is above performs better, whatever is below performs worse, right? So the pink one is this deep gravity, which is not doing so well. The purple one is a random forest, like a regressor, right? And all these like sort of orangey ones are the results from our Bayesian approach. So they work comparatively well in any metric that I can find, yes? And the nice thing about this is not only that, is that if now I apply it to like a different set of states that I didn't use to find my model, then in general, for most of the metrics, except for this one that only looks at large flows, it works way better, right? Why? Because these models, right, they give me the possibility to change parameters without changing the model in a way that typically other approaches won't. So it's kind of a very good example of how you can use these tools to, it's not that you learned something that was absolutely new because the gravity model was there, but you didn't quite know how to use it to make it competitive against like machine learning models that use way more features about the system. They are useless because you don't need them, but they still use them. I don't know. I mean, they use them because they can, but they don't actually need them. So with this was my last slide. Yes. So yeah. So the thing is that with this approach, using this inferential approach, we really compared to other models, which I didn't have to explain, to other approaches to symbolic regression, we have a way to combine these two ideas of how well the model fits my data and parsimony through my prior. And this turns out to be a very good option to understand, to get models from data. Also, I didn't mention this, but it also gives me a way to understand when I can stop considering the models. Well, I cannot hope to get any models from my data when the noise is large. This is I removed it. This is here, but I removed it because I didn't have time. But the thing is that using this inferential approach, right, I could compare simple models against the models that I find. And if my simple models give me a better, are more plausible than any other complex one, then there is no, I have to get more data points, right? I have to get more information because the information that I have is not enough for me to decide that really this dependency is exponential or whatever we have. So, okay, so with this, I just wanted to thank especially Roger. We co-direct the lab together, and we've been working a lot of time on the Bayesian machine scientist, a lot more than you think. If you think a lot, then think a little bit more, because it took us a long time. All of the people, we did a lot who worked on that, right? And especially Uriol and Luis, who worked on the what do you say, on the mobility part. And then Teresa and Gemma have been working more on the alignment part, but also like Tony, Harry, who I think is around here, Jordi, Oscar, Francesco, Manu, Jordi, and Ignasi, who put a lot of work, and these other collaborators who like helped us like develop some examples, especially Esteban, who worked on the mobility part. And yeah, and that's it. Thank you.